Our topic for today is imperfection in solids. Now, imperfection means which is not in proper behavior. But in solids, we don't say that imperfection is always bad. Imperfection can also be good. So, in a crystal, sometimes we add imperfect substances, some impurities. When you have learned about semiconductors or conductors, we make them by adding something to it. So, when it is not an orderly behavior, we call that imperfection. So when the crystal is being formed, during that time, sometimes the orderly behavior changes. Like if I am thinking that the constituent particles should be arranged in a proper way, they are not arranged in that way, then we say there is imperfection in that crystal. So now imperfection, there are of types, some types, which one is point defect, the other is line defect. Now point defect, you understand that this was the crystal. Say this is the crystal unit cell, and if there is something different in these points, then we will call it as point defect. And line defect will mean that if the particles have been arranged in a proper way, but this line is not proper. One or two particles are missing or some have been added, that will be known as line defect. We are emphasizing on point defect today. So point defect can be stoichiometric defect and non-stoichiometric defect. Stoichiometric defect is the one in which the stoichiometry of the compound doesn't change, means number of particles remain the same, but they have been displaced in some way or the other. So the first defect would be vacancy defect. Vacancy defect means supposing these were the particles arranged in the crystal, and there are few particles which are missing out of this. So these are the vacancy which have been created, that is, they are not present there. So obviously the entire crystal's density will decrease because few particles are not present there. So this will be known as vacancy defect. The second defect is called interstitial defect. Interstitial always means between anything. Interstitial particles are inter means between two. So interstitial particles are particles which are present in between. Supposing this was the black ones was the actual structure, but there are some extra particles which have gone right inside between all these. So we'll say this is interstitial defect. Now density is going to increase because particles should have been only these many, but some extra particles have come inside which are present in the interstitial spaces between the crystal, which will be known as interstitial defect, and density will increase. Third type of defect is called Fractal defect. Now in Fractal defect, this happens in ionic compounds, and in ionic compounds there are positive negative ions. So all these ions are supposing arranged, and one of the particle goes in between, like here interstitial. So it moves into the interstitial space, and generally the cation moves, because you know the cation is smaller in size, so that can fit inside this interstitial space, and that is why this particle, since it has shifted here, so where it should have been is called the hole. So this part is known as the hole. Number of positive ions and negative ions are same because this has only shifted. Numbers have not decreased. It has moved from here to here. So this particle is now present in the interstitial space, and so now the density remains the same because number of particles are still the same, and positive ions and negative ions are also same. So the whole crystal still remains neutral because positive and negative ions are present. This kind of defect takes place in ionic compounds with low coordination number, and the size of the cation should be small. Then this type of defect takes place. So Fractal defect takes place when the particle has shifted to the interstitial space. The next defect is short key defect. Now short key defect will take place when the vacancy is created by missing ions. So missing ions are A plus B minus, A plus B minus should have been here. So B minus is missing from this side, B minus is missing. From this side, A plus is missing. So both ions are missing, one positive ion, one negative ion. So there is a vacancy created by missing ions, and ionic solids with high coordination number will show this defect. Density will decrease because number of particles have decreased. There should have been these many, but 2 are not there. But electrical neutrality remains the same because one positive, one negative have gone out. So the compound, ionic compound remains neutral, but shows density as less than Fractal. So examples for this is NaCl, HBr and KCl, out of which you can see AgBr here also and AgBr here. So AgBr is the compound which shows both the defects, sometimes Fractal and sometimes short key defect. Now the other type of defect is known as non-stoichiometric defect. Now in this defect, the ratio of positive and negative ions gets disturbed, and that is why there is imperfection in that crystal. So first type of defect is metal excess defect, and this metal excess is due to anion vacancy. That means the anion is not there, so number of metal ions become more. So if there is a crystal, imagine when you are drawing the crystal, be sure that you draw A, B minus, A plus, B minus, then in this vertical line after A plus, B minus will come and so on. So alternate ions, positive and negative ions. So in this crystal, one of the negative ion is not present, that is the anion vacancy. Anion is not present. Instead of that anion, an electron takes its place. Now when the electron takes its place, the electron is delocalized, means it is not present at one place. It could be just moving. So while the electron is present here, it is able to impart color to the crystal, because you know we've learnt about how color is radiated. When the electron jumps to the higher energy level, comes back, it radiates energy in the form of color. So same happens here, the electron is able to impart color, and this hole which is created here is known as F center. So there is an anion vacancy here. Metal ions are more in excess, so it is called metal excess defect. Electrical neutrality is maintained because we have lost a negative ion, but electron is present, electron is also negatively charged, so it makes no difference. So electrical neutrality of the crystal is maintained. Another defect could be, the second defect is also metal excess defect, but it is due to interstitial cation. So the cation has one extra cation present in the interstitial site, in the site in between, and to maintain the electrical neutrality, there is also an electron in the interstitial site. So one positive, the negative one is the electron. So due to this, there is a defect. Electrical neutrality still gets maintained because one positive, one negative is already present here. Metal ions have become more in quantity, so it is called metal excess defect. Third defect is due to cation vacancy. Now understand this, cation vacancy means one of the cation is missing. So supposing A plus ion is missing from here, which had charge 1, and instead of that there is another ion which has A2 plus has taken its place. So this was missing. Here it should have been A plus. To neutralize both these places, the ion with higher oxidation state has taken its place. So total number of ions still remain the same. 1 plus 1 ion was absent here, but another ion which has higher oxidation state is present here. So at this place actually only A plus should have been present. Now to maintain this one, A2 plus is present here. Think something like, if sodium ion is missing here, Na plus ion is missing here, and we are putting here strontium 2 plus. So the ion charge has increased, which is going to balance both the things. So cation is missing and cation with higher oxidation state takes its place. Such a defect is called Cantine vacancy defect. That is, the cation had created a vacancy, but positive and negative entire neutrality of the crystal is maintained in this type of defect.